Okay, hello everybody. Good afternoon, all of you. So today we start with the quote. This is by Maya Angelou. If you don't like something, change it. If you can't change it, change your attitude. So everything based on attitude only, whether you like something or dislike something. Because there will not be something which is liked by everybody, or there will not be anything which is disliked by everybody. So everything depends on attitude. Okay, sometimes people ask me which subject is interesting. Every subject is interesting, right? Otherwise, that subject will not be there at all. Otherwise, there will not be people working in that subject. So it depends on how you are exposed to it and how initial teacher has made you interesting or something. If you are interested in some subject, it is because of some teacher. It is not because of something you born with that interest. So everything depends on the attitude. Okay, today we will see who is the birthday and Brattain, right? Walter H. Brattain. He is an American physicist who shared the Nobel Prize for Physics in 1956 for investigating semiconductors. So he is the father of transistors, actually, materials of which transistors are made, and for the development of the transistor. At college, he said he majored in physics and math because they were the only subjects he was good at. Some people who are extremely good in one, they will not be good at all, or they will be bad at some other subjects. But he is very good in both physics and math, and he became a solid physicist with a good understanding of theory, but his strength was in physically constructing experiments. His hands built the first transistor, and shortly this transistor replaced the bulkier vacuum tube. So previously, when we have studied BTech, actually we have studied vacuum tubes. When we have electronics lab, so we have used the vacuum tubes. But after that, they are replaced by transistors and completely they are disappeared. Okay, so they became extinct. Okay, so they replaced the bulkier vacuum tube for many uses and was the forerunner of micro miniature electronic parts. So for all the development of the electronics, computers and all, the transistor is the main thing. And he is the first transistor was built by his hands. Okay, today we will continue the centrifugal compressors. In the last class, what we had discussed is, so we have seen how the centrifugal compressor works, and then we have compared centrifugal compressor and axial flow compressor. Then we have discussed about the nomenclature of centrifugal compressor. So if you have seen, so I have told you from at the inlet, first it enters the bell mouth to make as much of air that can be sucked into it, and I will have a smooth uniform flow. And then there may be or may not be IGV, which are called as inlet guide vanes. And then it enters the eye of the impeller. So at the eye, first it enters the inducer of the impeller, inducer part, which is the transition piece, which converts the axial flow into centrifugal radial flow. And then I will have the impeller. And this impeller also will have impeller exit. It can be radial or backward chord vanes or forward chord vanes. And after the impeller, there will be vaneless space between the impeller and the diffuser. And then we'll have the diffuser. And then all this flow is collected in the volute casing with increasing area, and it comes out to the exit. So these are the things we have discussed. And then we have seen what are how the properties vary across the impeller and diffuser. So mainly the difference between impeller and diffuser, impeller is rotating and we give work to it. So that makes different. So in the diffuser, there will not be work transfer or heat transfer. So there will be delta Q0, delta W0. So dH naught is constant or dt naught is T naught is constant. Okay, because it is a diffuser, there will be decrease in the velocity and increase in the pressure. And stagnation pressure will decrease if there is friction, entropy increase and stagnation pressure will decrease in the diffuser. And coming to the impeller, because we are giving work, so dH naught has some work value. So H naught will increase. The stagnation enthalpy will increase. Stagnation pressure also will increase. And Again, because it is also like a diffuser, there will be pressure increase, density increase, and temperature increase. And velocity also increase because we are giving work. So kinetic energy increases. And that increase in the velocity, whatever is there at the exit of the impeller, we want to convert that into pressure, and that's why the diffuser is used there. Then we have seen the expressions for mass flow at inlet and exit. So inlet area can be expressed in two ways. Pi by 4 into d I tip square minus d I hub square. So the lower one, if you take hub, and upper one is tip. So pi by 4 into dt square. That is the annulus area at the inlet. And that can be written in terms of the blade height into mean diameter. So pi dm into h, or pi d1 into h. So one of the two ways you can, based on what is the data given, we have to use that particular area. And coming to the exit, so again, mass flow is equal to rho 2. Here in the inlet, the mass flow, the flow component is CA1, rho 1, A1, CA1. At the exit, rho 2, A2, CR2 will be there. That is radial component. To the radial component, the area through which it is coming out, that is pi d2 into b2. d2 is the impeller diameter, and b2 is the width of the impeller at the exit. So pi d2 b2. Then we have seen how the TS diagram will be, and we have defined the compressor efficiency that already we know in the gas turbines itself. So we have defined the compressor efficiency, and we have seen what is the expression for pressure ratio. And then we discussed about backward chord vanes, radial vanes, and forward chord vanes. And so the relative velocity comes out tangential to the blade. So in the backward chord vane, we are going to get the velocity triangle as acute triangle. For the radial vane, we are going to get right angle triangle. And for our forward chord vanes, we are going to get obtuse triangle. And then we have got the expression for the work. And so the work, which is U2, because assuming that it is flow is axial at the exit, CA1, CW1 is 0. So W is equal to U2 CW2 minus U1 CW1. U1 CW1 goes off, so U2 CW2 will be there. And from the velocity triangle, I can write CW2 as U2 minus CR2 cot beta 2. So I'm going to get U2 square into 1 minus phi 2 cot beta 2. And phi 2 is the flow coefficient, and W by U2 square is the work coefficient. So psi is equal to 1 minus phi cot beta 2. So if you draw the head flow characteristic, so we are going to get backward chord vane means a decreasing drooping characteristic. And for radial vanes, I'm going to get a horizontal one. And for forward chord vanes, I'm going to get an increasing slope characteristic. Okay, these are the things we have discussed in the last class. Any questions?
No, sir.
Yeah. Okay, we'll continue that. We are going to introduce some concepts today. Okay. One is slip factor. And another is called as power input factor. And surgeon and dimensional analysis, performance characteristics. Okay, these things we are going to discuss. Okay, so what is, and another thing, pressure. Okay, this is another one we will discuss. Okay, one by one we will go to. So coming to what is called a slip factor. And see the exit will component, which is CW2. Okay, so we design something for a particular value of CW2 I want, because the work is equal to U2 CW2, and it is designed like that. But somehow when it is calculated, right, or when it is measured, it is always found to be less than predicted. So for a few years they didn't understand what is happening like that. Okay, then they came to understand that there is what is called as slip. Okay, what is this slip? And if I have something like this, okay, a radial wind impeller, suppose if I take it this way. So if it is not rotating, something is entering at the center, so it is going to leave like this. This is called as through flow. It has to just go out from radially out. Okay, but because it is rotating, what happens is, because of the inertia, and it is when something is trying to rotate this way, it tries to resist, and there will be an opposite spin happens on every particle. It's like when a car is going forward, you are going backward, right? So everything will try to spin in the opposite direction because of its inertia, like this. Every particle will have an opposite spin induced. Spin induced due to inertia. Okay, and all these spins of the particles will form like an eddy. So it forms an eddy. This is called as relative eddy, due to the induced spin. So it forms like an eddy there. So this eddy, it is having velocity in this direction. That is tangential direction, but in the opposite way. So what happens actually here, I have the velocity this way, but here the velocity is in the opposite direction this way. Okay, so here instead of suppose if I take the velocities uniform this way, velocity distribution, but now what happens is, so in near to this, okay, near to this there will be opposite velocity, but near to this there will be velocity, induced velocity in the same direction. So there will be less velocity here and large velocity here. The velocity distribution will be like this. Instead of this way, I am going to get this way. Okay, forget about that, is not that important. So the important thing is there is an induced velocity in tangential velocity opposite to the direction of rotation. So if I have the exit triangle, okay, if it is radial vane, it is going to be like this. If it is a backward curved vane, so here what happens is, there will be, because of this tangential velocity which is induced in the opposite direction, so instead of this much of CW2, I will have less. So that induced tangential velocity is called as slip velocity, which is it can be written as Vs. So here this will be Vs. Now this will be C2, and CW2 will be only this. This is CW2 with slip. CW2, yes, I will write. In the same way here also, it will be like this. U will not change, right? So CW2 with slip, it will be less. Like this. There will be a decrease in the CW2 we get. So that is defined as what is called as slip factor. This is given by sigma is equal to CW2 with slip and CW2 without slip. It is CW2S by CW2 or CW2 minus Vs by CW2 or 1 minus Vs by CW2. Okay, so this is the way they defined what is called a slip factor. But now the question is how to quantify it. It's not enough if you qualitatively understand, because we are engineers and we are designers. We want to quantify everything. So how to quantify this slip factor? So this is done by a scientist called Stodola. So what he has done is he has taken a backward Godwin thing like this. And so he has assumed the relativity, the largest circle, whatever is possible, he inscribed here. So this is like an eddy motion, okay? So this is rotating in this direction. So the its velocity, angular velocity will be omega only, and he want to find out what is r here. So he has expressed this as some right angle triangle like this. And if I take the radius of the relative eddy as r, so this is the diameter 2r, and this is pitch s. That is the distance between two successive blades. So s is equal to, because impeller diameter is r2, 2 pi r2 by z. Z is number of blades. S is pitch of the blades. And R2 is impeller outer diameter. Impeller outer diameter like this. Impeller tip diameter like this. Okay, so S is like that. And this angle, this is beta 2. Because this is the exit angle, right? So this angle is beta 2. And if I take like that, so I can write this as 2r is equal to this is 2r, this is yes. If this is beta 2, just a minute. Oh, this is like this. So 2r is equal to Okay, here, this is the angle. Okay, maybe I have done in a different way. Okay, he has taken, okay, this is beta 2, this is S. So here, because this is beta 2, this is opposite side, 2R is equal to S sine beta 2, approximately equal to S sine beta 2. Okay, so here, then Vs is equal to R omega, where R is radius of the eddy. So from this, R is equal to S sine beta 2 by 2. Okay. That is Vs. And S is 2 pi R2 by Z. So omega sine beta 2 by 2 into 2 pi R2 by Z. So this 2 goes off, and omega R2 is equal to U2, blade velocity. So this can be written as pi U2 sine beta 2 by Z. So this is slip velocity. And then this is slip factor. This is 1 minus Vs by Cw2. That is 1 minus pi U2 sine beta 2 by Z. Okay, Cw2. And we have seen that Cw2 is equal to U2 minus Cr2 cot beta 2. Yesterday we have seen this. So if I substitute that here, again, similar to yesterday, if I take U2 outside, U2 common from this, and if I cancel U2 in the numerator and denominator, so this can be written as 1 minus pi by Z sine beta 2 by 1 minus phi 2 cot beta 2. This is the Stodola's model for slip factor. So this is for quantification. And for radial vanes, beta 2 is equal to 90 degrees. So sigma will be equal to how much? Phi 2 cot beta 2 will be 0 and sine beta 2 will be 1. So 1 minus pi by Z. This is for radial vanes. And if I then okay, for radial vanes, 1 minus pi by Z. And for backward chord vanes, for beta 2 is equal to 45 to 90 degrees. So Stanage has come with a formula. It is like 1 minus 0.63 pi by Z. Approximately sigma is equal to 1 minus 0.63 pi by Z. Okay, so this is an empirical one. It is approximately, you can do like this. Okay, this is about the slip factor, and usually sigma is approximately 0.9. If you want to do a rough calculations and all, sigma is 0.9. So in the problem, if it is given, okay, you can use the value. If it is not given, you can take sigma as 1 only. Okay, you need like efficiency and all. If value is given, you take it, otherwise you take it as 1. So this is about the slip factor. So there is another thing called as work input factor. Work input factor. So suppose for some pressure ratio, you have to supply some work. But because of disk friction, sometimes this is called as windage loss. Because of the disk friction, the required work is more. And so here the required work is written by multiplying by what is called as work input factor. So usually this is represented as small psi. That work coefficient is different, that is capital psi, and this is small psi. Okay, just it is a notation, right? So work input factor, this is approximately is taken to be some 4% extra work I have to spend. Okay, psi is equal to 1.04. So here, if you take the work, W is equal to U2 CW2 minus U1 CW1. So if inlet is purely axial, CW1 equal to 0 and W is equal to U2 CW2. And mostly in aircraft applications, because we are mostly doing aircraft applications, radial vane compressors are used, where CW2 is equal to U2. And here, that's why many times what they do is sigma is expressed as, instead of CW2S by CW, so they use CW2 by U2. So this is CW2 with slip, whatever is that. But ideally, CW2 should be equal to U2. So sigma is defined as CW2 by U2. Or CW2 is equal to sigma U2. Okay, so here W is equal to, if U2 here, U2 into sigma U2, which is sigma U2 square. But using work input factor, the W is equal to psi sigma U2 square. Okay, this is the expression used. As I told, if psi is given, you use it. Sigma is given, you use it. Otherwise, you can take it as 1, default values. But otherwise, you have to use those values. Okay, so this is the work expression. But when you come to pressure ratio, yesterday we had derived this P03 by P01 R is equal to T03 dash by T01 is equal to 1 plus eta C W by Cp T01 to the power of gamma A by gamma minus. Okay, this is the way we defined. So this W can be substituted here. So R is equal to 1 plus eta C psi sigma U2 square by Cp T0 to the power of gamma A by gamma A minus. Okay, this is important relation. The expression for pressure ratio across a compressor. This is true for same expression for both. Okay, not this. I should not say like that. Okay. The previous one, this expression is same for centrifugal and axial compressors. But the W is equal to psi sigma U square. It is only for centrifugal compressor. So this is true for centrifugal compressor, but this is true for both centrifugal and axial flow compressors. Okay, that we are going to use in the next chapter. Okay, coming to now this R here. And so what are the factors affecting pressure ratio? Pressure ratio R. Okay, so we got R is equal to 1 plus eta C psi sigma U2 square Cp T naught 1 to the power of gamma A by gamma A. Okay, so if you see here, eta C, I cannot do anything. It is efficiency of the impeller or the compressor. So this is by fabrication it comes. And psi, this is due to disk friction, which I cannot do anything. And slip factor, it is also by nature it comes, right? Because of it is rotating, there will be opposite spin, induced velocity, everything will be there. I cannot do anything. And Cp and gamma, it depends on the fluid properties, okay? So if you change fluid, the pressure ratio changes. But again, if it is air, I don't have any thing on that. And T01, this is also, it is ambient temperature. And nothing can be done about it. So there is only one component, which is U2. Affects the pressure ratio. U2 is the only one that affects the pressure ratio. So as U2 increase, pressure ratio increase. Okay, how much we can increase? This is limited by centrifugal stresses. This is limited by centrifugal stresses. So approximately U2 max is 350 meter per second with steel blades, mild steel. But it can be increased up to 450 meter per second with titanium blades, which can withstand higher stresses. Okay, this is the way. And so 1 plus and eta C sigma psi U2 square by Cpt naught 1 to the power of gamma A by gamma A minus 1. So eta C is approximately, I can take 0.85 to 9.9. Okay, 0.85% I can, 85%. And sigma, I told it is approximately 0.9. And psi approximately 1.04. And Cp 1.005 if it is air. Kilojoule per kg Kelvin. And gamma A, that is 1.4. So all are fixed. So you can just, and T01, the ambient temperature, you can take 300 Kelvin. So you can find out what is the pressure ratio I can produce. Anybody, if anybody has calculator, can you do it? Is anybody trying? Is anybody trying?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, right. You try with 350 and also with 450.
$26.63, I guess.
No. I think, no. Here, you have to put 1005 because it comes joules. Psi U2 square, it will come in joules. This psi sigma U2 square, it will be in joules. So CP in joules should be 1005.
1.032.
How much?
1.083.
1.0323.
Pressure ratio.
Yes, sir. For 350 meter per second.
Okay, you try 450 also. There is something wrong.
Sir, for 450 it is 1.13, sir.
Which one?
1.13, sir.
0.13.
1.13.
But there is something wrong. Have you put gamma A by gamma A minus 1?
Yes, sir. So I will do one for
I am getting 4.47.
R is equal to 4.47 with 350 or 450?
450, sir.
450, right. 4.47. Huh?
Yes, sir.
You try with 350.
Now 2.665, sir.
Yeah. Why other people got different answer? This is good. Okay, this is the way we get. If I have normal 350 meter per second, I'm going to get the pressure ratio of approximately 3 or around 3. But if I have titanium blading, so if I have 4.47, I can go up to 4 pressure ratio. That's what I was telling at the beginning. The pressure ratio can be up to 4. Okay, with a single. See, other people, please check what is wrong. Actually, I don't know what.
Got it, sir.
Got it? Okay, what is the mistake you have done initially?
Sir, I did gamma A minus 1 by gamma. Sir.
Yeah. That's what. That's why I got doubt. So
Yes.
because normally we take pressure ratio to the power of gamma minus 1 by gamma. But
Yes.
here we are calculating R. So it is temperature ratio to the power of gamma by gamma minus
Yes.
1. Okay. So this is the way we get. So this is the only factor which is affecting the pressure ratio. So the more velocity or RPM you can have, and with the more size you have, because U2 depends on the RPM and the diameter. Okay, so the size increases, the U2 increases, or the RPM increases, the U2 increases. So by increasing one of them, you can have the increase in U2. So you can have the pressure ratio of this range. Okay, this is about this. There is one more thing I was telling about pre-whirl. Okay, this is related to what is called as IGV, inlet guide vanes. So here, when I have something like this, so this is CA. Okay, so this is C1 equal to CA1. Sorry, this is V1 and W1. This is the inlet triangle. So as I was telling, the inlet triangle for the turboprop or something like that, I was doing it, right? So if it is inlet is coming axially like this, and because of the rotation of the blade, so I will have V plus U equal to C. So I'm going to get a triangle like this. So as I was telling in the turboprop like thing, in the same thing, it may happen here. So this U1 is 5D1N by 6. And the D1 it changes, right? So D1, okay, mean is here, but hub to tip, the velocity changes. Okay, so if I take for hub, it may come like this, and for mean, it may come like this, for tip, it may come like this. So the inlet triangle changes, right, from hub to tip. Am I clear about that? So this is U1 hub, and this is U1 mean, and this is U1 tip. So V1 also, V1 tip is this. This is V1 mean, and this is V1 hub. Am I clear about this? So beta 1, this is beta 1, this is tip. This is beta 1 mean. This is beta 1 H. So the inlet angle changes, the relative velocity angle changes. So my blade also should be designed in such a way that at every radius, it goes smoothly into that. So because inlet angle is changing from hub to tip, it has to have a twist. I have to bend it in such a way that at every radius, it goes smoothly over that. Am I clear about this particular concept? Inlet is axial, C1 equal to CA1, no CW1, no whirl component. Purely axial inlet. Okay, and so I have drawn the triangle, and the triangle, the base is U. Okay, I can tilt it in the horizontal way, base comes horizontal, right? You can do that. But because it is entering in this way, I wanted to draw the triangle like this. It need not be like that. So U can be like this, and CA1 like this, and you can have triangles this way. You can draw this way also. Okay, so this is U. And U1 H, U1 mean, U1 tip, like that. And this is CA. So I will have V1 T, V1 mean, and V1 H. This is U1 H, and U1 mean, and U1 T. Like this I can draw. And these are the angles. Okay, I have to give angles always with respect to tangential component or with U. Okay, so this is beta 1 tip, this is beta 1 mean, this is beta 1 H. So this inlet angle is changing, and because of that, the inducer blade, which we have shown in the last time, I have shown a figure, right? So at the inlet, it is quite bent. It is to make sure that it enters smoothly over that. Is that point clear? Somebody respond. Otherwise, I don't know whether you are listening or not, or whether people are there or
Yes,
the
sir.
audio is working or not. Okay. So to check whether audio is working or not, I ask sometimes small questions. Okay. Now you can see now V1T is the maximum. And so that's why even when CA is subsonic, V1T may become supersonic, which may create shock. Okay, so I have to be careful. I have to see that there will not be shock. So the critical one is Mach number with respect to V1T. Okay, that is V1T by root gamma r T1. Okay, I have to check this. Okay, whether this is below or beyond, above Mach number 1. Okay, so if it is, if you assume that or expecting that there may be a shock, so I have to do something about it. Okay, so here mass flow is equal to rho 1 A1 CA1. Okay, so I don't want to change the mass flow. Same mass flow is coming, right? So what I do is I put what are called as IGV. Okay, what will IGV do? So now I have so at the tip, suppose I have this is the velocity triangle. Okay, so here what I do is I will put an inlet guide vane in such a way that this sends the air by a little bit deflection. It introduces a whirl component. So it comes like this. Instead of coming axially, okay, this is coming axially for the IGV, but it bends the thing like this. Okay, and this is called as angle of pre-whirl because it introducing some whirl component. And now this is CW1 and this is CA1. Okay, CW1 is the pre-whirl component or whirl component at the inlet. So because of that, what happens now? U1T will be same, right? So my triangle will change to this. So V1T gets reduced because the base of the triangle, it will not change because the speed is same. So my triangle gets modified and V1T gets reduced. So this is V1T with pre-whirl less than V1T when C is axial. Like this. Is my point clear?
Yes, sir.
Okay. So IGVs are used to introduce some whirl component at the inlet, which is called as pre-whirl. And okay, we are avoiding shock, but anything is at the loss of something else. Okay, what happens? Now my pressure ratio depends on W, which is U2CW2 minus U1CW1. And previously U1CW1 is 0. Now CW1 is not 0. So this will be W now. So my R is equal to 1 plus eta C psi, eta CW by CPT naught 1 to the power of gamma by gamma minus 1. So this W gets reduced. So R gets reduced. The pressure ratio that is developed gets reduced. Is my point clear?
Yes.
So it is at the cost of pressure ratio. It avoids the shock at the inlet by reducing the Mach number at the relative Mach number at the inlet, but it introduces a reduction in the pressure ratio. Okay, this is about pre-whirl. Okay, and so these are the things which are very much needed. So again, it depends on the problem. In the problem, if there is no IGV, if there is no pre-whirl, you have to take the inlet is axial. Okay, inlet is axial only, always the main inlet. But if I keep some IGV in between, then it introduces the whirl at the inlet. Okay, then we will see what is dimensional analysis. So for doing dimension analysis, because as I told always, whenever I want the characteristics of any experiments, so if there are more number of variables, I'm going to get more number of graphs. To reduce the number of graphs, I always do the dimension analysis and draw the graphs between dimensionless parameters. Okay, so that reduces a lot of work and experimental burden. Okay, so but we have to be very careful about what are the performance parameters. Okay, what are the performance parameters? Okay, at the inlet, I have pressure and temperature. And at the exit, the pressure and temperature. And then the mass flow. And also the size and the speed. Okay, so these are the main parameters which are the performance parameters of a centrifugal compressor or axial compressor, whatever it is, and even for turbines also. So these are the general things. And how to do the dimensional, get the dimensionless parameters. So we have various methods like Rayleigh method. What is the other one which is popular?
Buckingham pi method.
Buckingham pi theorem. Like this. Okay, so if I want to do that, I will not do all those things. With simple logic, I will do it. Okay. So P01, T01, P02, T02, D, N, and mass flow. Okay, so first we have to find out what are the dimensions. Okay, can you tell me in MLT? Okay, so what is the dimension for pressure?
ML minus 1, T minus 2.
M, L minus 1, T minus 2. Do all of the people agree?
Yes, sir.
And here for temperature, because it is coming another one, like MLT theta also will be there. Instead of that, I will keep RT not 1 and RT not. If it is RT not 1, so what is going to happen to this? Anybody try?
L2, T minus 2.
Yeah. This is like velocity square. So P by rho is equal to RT, right? And P by rho is C square by 2, right? If you remember Bernoulli's equation. So these are the units of velocity square. So L2 T minus 2 meter square per second square. Okay, so this is also L2 T minus 2. And D, length only, right? And N, RPM,
T minus 1.
T minus 1.
Minus 1.
And M dot,
MT minus 1.
MT minus 1.
Minus 1.
okay, these are the things. So here, so I have to, because there are three fundamental dimensions. Okay, there are three. And the total are 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to get 4 non-dimensional parameters. And first I have to select 3. Okay, with others I have to make the non-dimensional things. So what I do is I will take one with all MLT and one with LNT and one with only L. Okay, so I will take P01 because this is the inlet condition, right? I am taking that as one, and RT01 having L and T only. There is no M. Now I have to take only L, so this I will take. So P01, RT01, and D. And with these three, I have to take the others and I have to make, because 3 are over, the remaining 4. With all the 4, I have to take with each one non-dimensional parameter. So if I take P02, right? So with one of these, I can take. So P02, if I take, divide just by P01, I will get one non-dimensional parameter. Okay, so ML minus 1 T minus 2 by ML minus 1 T minus 2, I am going to get one non-dimensional parameter. This is R. R. I will write actually P03, P0, okay. Okay, R, pressure ratio is one of them. And then if I take RT02 and dividing this RT02 by RT01, I'm going to get another second one. And this is temperature ratio. Actually, this is replaced by efficiency of the compressor. And the third one, non-dimensional RPM. Okay, if I take N, which is L, N is T minus 1, right? T minus 1. So if I want to eliminate T minus 1, how to eliminate T minus 1? So I have to eliminate T. Okay, I use RT02 to eliminate T. So if I take the root of RT02, it becomes LT minus 1. So if I divide by LT minus 1 by root RT01 by LT minus 1, so this gets cancelled. I am going to get L. This L is to be cancelled. So divide by D. Okay, divide by D. So L by L. So this becomes non-dimensional. That is N by D root RT0. Okay, this is 1. Is it clear?
Yes, sir.
Is it right what I am doing? T minus 1.
D will be in the numerator, I guess.
Yeah. D, this is 1 by, yeah, D should be in, that's why there is something wrong, okay? Because here I got 1 by L, I have to multiply by L, so ND by root RT0. ND by root RT0. This is the third one. And fourth one, I have to take mass flow, I have to non-dimensionalize this. And mass flow is MT minus 1. And first I have to eliminate M. How to eliminate M? Use P01. Divide by P01. So divide by M, L minus 1, T minus 2. So M goes off. L minus 1 means L will be there in the numerator. T minus 2. So T plus 2 minus, so LT. Am I right?
Yes, sir.
So in a LT, I have to eliminate T using RT02. If I want to eliminate T, multiply by root RT01, right? Multiply by root RT01. So it will become LT minus 1, I have to multiply. So T minus 1 goes off. So it will be L square. How to eliminate L square? Divide by
D square.
D square. So this is the fourth one. So I will have pressure ratio, efficiency, and ND by root RT01 and M dot D square by, sorry, M dot RT0 root RT0. M dot root RT01 by D square P01. Okay, so these are the 4 non-dimensional parameters we come across. And if you see this dn, this is like pi dn by 60, that is rotational velocity. Okay, this represents rotational velocity by root RT01. This is like sonic velocity. So sometimes this is called as rotational Mach number. rotational. This is like Mach number, right? So this is some rotational Mach number. And if you come here, m dot is right rho ACA, right? Root RT naught 1 is like P naught 1 by rho naught 1. So this is P naught 1 by rho naught 1. It comes like density, and d square, it is like A. Okay, this is like P naught 1 by root RT naught 1. What happens is it acts like 1 by sonic velocity. Okay, so here P naught 1 is rho naught 1 RT naught 1, right? So it is d square is like A, and P naught 1 is rho RT, and here root RT is there, and rho gets cancelled, A gets cancelled, and one root RT gets cancelled. I will get root RT here. So I'm going to get CA by some root RT. It is like a flow component by sonic velocity, and it is also like Mach number. So this is called as flow Mach number. Both are like Mach numbers only. One is rotational Mach number and another is flow Mach number. Okay, so these are the things. So if you see here, pressure ratio, efficiency, and ND by root RT naught 1, and m dot root P naught 1 by d square. Sorry. Like this.
Sir, in the
In the other way, okay, the other way, I think. M dot root RT naught 1 by P naught. D square P naught. Okay, so this is the way we get. These are the four non-dimensional numbers. But here, if I take air as the working fluid, okay, then R is constant. Okay, and if experiments are done on the same impeller, D is equal to constant. So if I eliminate them, I will get R, efficiency, n by root T naught 1, m dot root T naught 1 by P naught. Okay, these are the parameters we will consider. Okay, this is something in confusing sometimes, because if you see the hydraulic pumps or turbines, right, there we use specific speed. Is specific speed dimensional number or non-dimensional number?
non-dimensional numbers.
But if you see, the specific speed for pumps is n root q by h power 3 by 4.
It's dimensional then.
Dimensional.
This is for pumps. And n root p by h power 5 by 4, right, for turbines. These dimensional, right? But actually, they are not dimensional. They are derived from non-dimensional things, right? Actually, it is not h power 3 by 4 or h power 5 by 4. It will be gh. It will be gh like that. And even diameter also will be there in the calculation. So assuming that g is constant, we remove that, and d is constant, we remove that, and finally we come with n root q by h power 3 by 4 and n root p by h power 5 by 4. So it comes from non-dimensional groups, and but this looks like dimensions because we are neglecting those things which are constants. Am I clear about it?
Yes, sir.
Okay, so these are the performance parameters. So between this, actually, I have to draw the graphs. So if I do the performance characteristics, and there are 4 parameters, how to do that. So what we do is, I will take mass flow here and pressure ratio. Okay, I can take P0 3 by P0 1, actually pressure ratio R is equal to. If I draw this, what I'm going to get is I'm going to get a graph like this. Okay, for a given pump with air. So this is the way we get. But here, what happens is, though it comes like this, the range this side is unstable. We cannot run this side very much. So what happens is, so if you take this side, as mass flow decrease, pressure increase. As I was telling previously, P is equal to gamma QH, and Q and H are inversely related. And Q is mass flow and H is pressure ratio. So here, as mass flow decreases, pressure increase, everything goes well as far as this portion is concerned. But when you come to this way, okay, if I come this way, what happens is, there will be, the operation will be unstable. Okay, physically what happens, I have taken this is the operating point, gradually decrease, or the throttle, you close it. So gradually the mass flow decrease and there will be increase in the pressure. It goes like this. And after this point, actually pressure ratio has to reduce. But what happens is, okay, this is rotating, and here this is the throttle. So when I reduce this, there should be decrease in the pressure, and that decrease in the pressure takes place here. Sorry, the decrease in the pressure takes place in the impeller, but here the pressure is high. So what happens is, it will try to have a reversal of flow. So it is like just reducing means it actually tries to obstruct, and there will be a reversal of flow takes place. Right? But the flow is coming this way. So here what happens is, so it tries to reduce here, but that flow and the new flow that comes, so it just shifts to this point. But again, the flow, it cannot go because the valve is closed, so it tries to go like this, the mass flow decrease. So actually there will be a complete oscillations of flow takes place. And which results in vibrations and instability and damage to the impeller. And this is called as surging. This happens both in the pump or compressor or centrifugal or axial compressor, whatever it is. So this is called as surging. Surging is an unstable flow, and which creates a lot of oscillations in the flow and the reversal of flow and the damage to the impeller. Okay, this is surging. So what happens? for a particular speed, there is a particular range of flow that can take place. And here also, there is what is called a choking. I cannot increase the flow beyond some point. So that is called a choking. So the complete operation range between is surging to choking. Okay. So here, if I draw it for different speeds, and here it comes like this. Okay. This is the way. For different non-dimensional speeds, I'm going to get, this is at particular speed, I get like this. Another speed I get like this. Another speed I get like this. Another speed I get like this. Okay. And all are stopped by the surging point. This is called as surge line. This is called as surge line. And there is one more parameter left out, that is efficiency. And for this curve, the correspondingly, I will get a curve like this, efficiency curve, okay, between this particular range. And for this, again, there will be, for this particular range, I'm going to get another efficiency curve. Like this, I'm going to get efficiencies with respect to speeds. Okay, these are the centrifugal compressor performance characteristics. Is this clear? At every particular speed, I'm going to get a curve like this, and different speeds will get different curves. And on the left side, it is restricted by surging. On the right side, it is restricted by choking. So only a small range of mass flow is allowed. Okay, so actually at low mass flow, I cannot run it much time. When you are starting, actually mass flow will be less. I have to quickly increase the mass flow so that it will not be in surging for more time. Okay, so you cannot avoid it, but you can just go fast over it, and then you can have the running between these two mass flows. Is it okay?
Yes, sir.
Yes, sir.
Okay, tomorrow we will solve problem, right? So today we'll stop here, and we'll go for the story.
Yes, sir.
I think it is not coming here. We'll just so we'll see one or two great people. Actually, many times people say that my background is very bad. We are very poor, and how can I be successful? How can I grow in my career? And many people are having money from their parents or grandparents and the family and all that. That's why they grow. But if you see, 90% of the people who are successful, who became highly rich, are very poor at the beginning. Okay, some of the examples, if you see, there is who is called as Andrew Carnegie. Okay, he is called as the father of steel. He is a steel tycoon, right? He has multi-billionaire, right? So in America, okay, now he's not there, but he's very, very famous, Andrew Carnegie. And the steel tycoon who grew up in a one-room weaver's cottage. He has he grew up in one-room weaver's cottage, Andrew Carnegie. His first job was at age 13 as a bobbin boy, changing spools of thread in a textile mill, right? Bobbins, that spools, he used to change it. So that is the way he worked, changing spools of thread in a cotton mill 12 hours a day, 6 days a week in Pittsburgh cotton factory. So he worked like that. So that is the background of him. So you can see he is that Andrew Carnegie working in the spinning mills. And by 1889, Carnegie Steel Corporation was the largest of its kind in the world. He donated millions to the New York Public Library, established the Carnegie Institute of Technology in Pittsburgh, which is now known as Carnegie Mellon University, created the Carnegie Foundation for the Advancement of Teaching, and formed the Carnegie Endowment for International Peace. Okay, so that is the man he became later. So there is another person we'll talk about, the retail giant who had to milk cows and deliver newspapers, and he is Samuel Walton. He milked the family cow, bottled the surplus, and drove it to customers, and afterwards he would deliver Columbia Dairy Tribune newspapers on a paper route. In addition, he also sold magazine subscriptions. Okay, so that is the way he has grown up. And so Forbes is the magazine who tells who is the richest among the world, and he gives the ranking, the first richest, second richest, like that. So Forbes ranked Samuel Walton as the richest person in the United States from 1982 to 1988. At the time of his death in 1992, he had 1,960 Walmart stores, employing 380,000 people, and clocked annual sales of about $50 billion. Okay, so he has grown to that stage. Who has milked the cow and used to sell the milk and distribute the newspapers, he became like this. Okay, so there is nothing can stop anybody who want to grow, right? So that's what I want to convey. Okay, thank you very much then. We'll meet tomorrow's class.
Thank you, sir.
Right. So tomorrow be ready for solving problems. Okay.
Yes.
See you then.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.